Great, thank you. Hello, everyone. Thank you for having us at Talmo. Thank you for that presentation. So we're in the same vein. We're looking at um, supporting learning as opposed to performing for a test. So it's a good follow on. So my name's Peter Johnson. I'm a lecturer in engineering at Imperial College London and presenting work that's in collaboration with Phil Ramsden, who's a mathematician in the maths department at Imperial. Marcus Messer is a postdoc on the project working on the computing side. Karl is a mathematician who was a postdoc with us for 3 years, so it's a lot of his work here. Amelie Lawn is a lecturer in mathematics as well, and some of her work is here. So we're talking about Lambda Feedback, supporting student learning with automated formative feedback. So this is work that's been going on a few years at Imperial College, and I'm happy to share with you. So what I'll do is I'll start with a little video of what's going on just to make it concrete, and then give you an overview of the presentation, what we're going to talk about. But it's self-study and it's automated feedback. So you can see hopefully a video here. There's a task on the web, and a student is writing in their answer. They're getting live feedback on how that's interpreted. And then when they're ready, they press the check button and then they get feedback. In this case, they're incorrect and they're told why they're incorrect. So this is formative feedback. It's timely, it's specific, it's actionable, and this is the general vision. And so this is happening. This is a video of what's deployed to students now. And so this presentation is all about that. And by the way, I'll very much welcome interruptions as well as questions at the end. So what I'll do is start by saying, what is the feedback problem? Why are we doing this? And then about the platform itself that I've just showed you called Lambda Feedback. And then the microservice principle. So the idea that the feedback that was provided there was obtained by calling an external service. I'll say more about that. And then I'll show you some case studies of some of the feedback algorithms that have been deployed on this platform using that architecture. So starting with the feedback problem. So we're looking at self-study. So undergraduates, we're talking here about mathematics students, but actually we're talking about any student, and the relevance of it being at Talmo is that it includes, and all of this presentation will be focused on mathematics in the sense of the maths department, but also mathematical methods used across especially physical sciences and engineering. And all of these students are spending most of their time in self-study, and that involves getting stuck. And it's an essential part of the process of studying is getting stuck, reaching an impasse. So we don't want to omit or obviate those impasses because they're part of the learning process, but they can sometimes go on too long and cease to be productive for learning. And so at that point of the impasse, the student needs some good feedback. So something that's timely, specific, and actionable, depending on your theory, goal-orientated, and of course it needs to be accurate, and that can help them continue with their learning. So this is the feedback problem in general that we're familiar with in education, and we're looking at automating this, which of course people have done a lot of and are giving a certain take on that today. So in a simplistic sense, we're taking something from a student, call it their submission, and some other information, some context, some reference information. So typically this is the student's answer and the teacher's answer, but it could be something more general. Then we need to evaluate that somehow to decide whether the reference criteria are met or not, and then generate some feedback. So this is a kind of a general frame to think about what I'm presenting today. So initially, we were really just interested in how to do that evaluation. We used tools like Mobius that was presented earlier, and wanted to generalize this to use other languages. So our initial interest was here in the evaluation, but we find that there is this hidden cost, which is that the evaluation only works if you have enough reference information. So an example of that is that an example would be the square root of gravity divided by volume. It's just a real example. Is that equal to the square root of gravity divided by the square root of volume? And the computer algebra system that you might use to evaluate will say no, because you didn't explicitly declare that both gravity and volume should be assumed positive. So will every teacher go into every question and provide enough information? And then, of course, if you do succeed in all of this and you can give feedback, it's actually not straightforward. Even though we have good literature on what is good feedback, we don't have good research or literature on what is good automated feedback. And so that's something that we might be able to collaborate on if anybody here is interested in that. And so I've put these little pink collaboration opportunities on each slide that I won't reference again, but if you look out for them, I'm interested in your views. So at this point, it would be on the research here. So this is the general idea. But of course, if you want to do this in practice, you need to deploy, you need the plumbing. So how are you going to get the students' input without them doing any extra work? So it's got to be handwriting in maths, and it's got to be smooth for them. And then how do you actually get all of this information together? You need a platform. So what I'll talk about next is the Lambda Feedback platform that we've developed. If you like, it's an analogy to Mobius that was mentioned earlier, or Stack that I think is common in this community. With some distinctions. Firstly, just to give a bit of perspective, I've deployed it on one module in 2022, January 2022, and it's since grown to be used across Imperial College. So millions of feedback events like that video that I showed you every year, and lots of content. So what I'm reporting on here is kind of experience of deployment at scale. That's the point here, rather than a kind of a prototype or an idea. So just a quick guide to the platform itself to show you the context in which we're providing feedback, as well as the task and the feedback. There's these kind of work solutions that can be revealed step by step, and that's popular with the students for seeing only enough, not seeing too much. And then from the teacher's point of view, there's an editor. So this is Markdown based with LaTeX. So you've got a LaTeX preview, then you just click a button and publish that. You've got a single source of content that will generate the web view that I've shown you, and a LaTeX generated PDF for an old school tutorial sheet for those who want that, which in our case is about 20% of our users. And then you can download it as LaTeX, so you can get it all out again. You're not locked in. Then also from the teacher's point of view, you can get the data on how students are using this. And because we use it for their kind of main study, that's quite insightful in terms of seeing engagement levels and progress levels. So some examples here are module data. So this is typical across the college. You see some students keeping up and some, getting gradually more behind. Diagnostics on a particular task and how people are answering it and how you might provide feedback. I'll say more about that. And then student level information that can be used for pastoral care. So the focus today is on the mathematics. So I'll skip that and just briefly show you that students can use a canvas, comment threads, feedback on essays in GCSE English, just to show you it goes beyond maths, and chatbots if the teacher chooses to turn it on. So that concludes the first part of the presentation, saying we've developed this platform and deployed it, and this is the context in which we're delivering feedback. So I want to talk about the architecture behind providing the feedback. So I've got a basic sketch here of a nice software system split into modules. You could imagine this is something like a web client and a server and a database, and then some kind of module for generating feedback. And the principle behind Lambda Feedback is to take the feedback generating part and take it outside of the platform so that it's completely independent. So our platform doesn't generate any feedback. It calls external services which generate the feedback. So the reason we do that is so that the feedback generation is decoupled, so that could use any computing language, any type of runtime environment or infrastructure. So we've been using SymPy a lot, and we started using Wolfram, but you could plug in any software you like. It's also reusable by other platforms, so that if you generate a good algorithm for giving feedback, like the one I showed at the beginning, then that could be available to other platforms. So we've currently got a relatively new collaboration to make a standardized API for microservices in education, so MuEd, where we're trying to standardize this interface so that if you make a nice algorithm, that it could be called interoperably by lots of systems. So this would mean people like the Talmo community could focus on a task of their choice, make a good feedback algorithm, and then that there's a much lower barrier to getting that out there and having impact, because you only need to do the algorithm and not the whole platform. So this is the architecture. And so I want to show you some examples of those external services. So we have about 20, but these would be the ones I would choose for interest. And I'll highlight three in particular. So I'll start with the middle one, which is the Buckingham Pi theorem. That's the one that I showed you in the video at the beginning. This is a specialist task type, and we used the theory, which is basically linear algebra, backwards to evaluate student inputs, and always, despite the infinite number of inputs, always give qualitative feedback on why or how an answer might be incorrect. And then another example is the comparison of algebraic expressions. I'll show you that in more detail, and then evaluating mathematical proofs. So I've chosen these two because these are the most mathematical ones that we do. So I thought it's of most interest to Talmo. So I'll start with this one, compare expressions. And so it's a busy slide, but don't worry, I'll go through it bit by bit. So here is the same diagram that I started with. So we're taking a submission from a student, and this is an example, and we're taking some reference from a teacher, which in this case is just a correct answer. And then we're evaluating whether they're equal and then providing feedback. So with experience over the years of developing this evaluation function called compare expressions, we've abstracted the process into 4 steps. The first one is that selecting a context, such as whether or not there's physical units. In this case, it's basic algebra. And then the big part of the problem is the parsing. So the things listed here. So here's an example of what was turned from handwriting into code. You can see an explicit multiplication here, but an implicit one here and here. And that's been taken care of here. So we're making good progress. And then when you evaluate, there's different types of evaluations. So equality is what you first think of, but you may want to compare structure, or there may be other criteria such as, a derivative or comparison of derivatives or something more exotic or elaborate. And then currently our feedback generation process is basically to concatenate the different pieces of feedback that come up. So this is something that we've got a database now of more than 500,000 of student inputs. So if you'd like to help us tear that apart and look into it, then we'd love to share. And here's one example that I can show you. So the students put this expression in, the teachers put this expression in, and because it's processed by a computer algebra system, we can get the abstract syntax tree. So they're different. So the first answer is it's incorrect, according to the computer algebra system. Hopefully that's accurate. In this case, it's accurate. And the next step we're doing, which is not deployed, this is kind of at the research stage, is could we find out why or how there's a difference between these two trees? And there are algorithms that can do this. So if we look at the minimum edits to the submission to make it equal to the reference, then we could say, potentially say what's wrong and give some better feedback. So in this case, the minimum number of edits is 22. So that's great. We can get from the student submission to the answer, but I'm not sure what good feedback we could give a student by telling them those 22 edits, because really they need to get the answer through the process of solving the task rather than through the process of editing and reverse engineering to get the answer. So it's progress. You were kind of helped frame the problem, but if you get 22 edits, what do you do with that? How do you actually produce good feedback? But this one is also interesting because if I recast this expression in a different form, you'll see that the student's N was a K in the teacher, but really they're the same thing. So they could have been, if we created the correct context, they could have been recognized as equal. And really it's just missing an I here. So the student has made a mistake, but we could have done better at automatically identifying what the mistake was. And even then, it's not easy to say what would be good feedback, but we would give feedback at that point. So large language models would be really good for this because they'd be really good at seeing that difference, making a suggestion, potentially being wrong, but then we could ground it in the computer algebra system and test whether the suggestion is right before relaying it to a student. So this is a kind of area of development. At the moment, the live in the loop feedback would just say, you're incorrect. But hopefully in future, we could give much more qualitative, granular feedback, which we would, as I said at the beginning, somehow consider good if we've got some criteria for that. So that's compare expressions as a case study. And I want to move on to show you some work done by Amelie and her collaborator Aran. So what they've done is they've asked students to provide a complete proof. So this is their first year undergraduate mathematics. They're doing formal proofs, and they're using LLMs in quite a complicated way that they've tested quite rigorously to provide feedback to the student. So there's a few points I want to make here. The first one is that Amelie and Aran worked completely independently and nothing to do with Lambda Feedback, and generated their algorithms and then wanted a way to deploy it to the students. And that's where our collaboration came in. Because we have this model of an external microservice, we could simply hook up their algorithm to the existing platform that has the modules and the enrollments and all of this plumbing, as I called it, which is expensive to build. That was all ready, and we could literally just plug in this algorithm and get it go and deploy it. So that's one of the important points here. Then briefly, you can see that there was a problem where they're asked to provide a truth table, and they've handwritten this, and it's been translated and then gobbled up by the LLM, followed all the rules in their prompting and given some feedback. And then another example here, a bit more familiar to some. So the P&O axioms, well, not familiar, but more kind of prosaic, I think is the point here, and feedback, just to give you an idea of what's going on there. So they've done a in-depth analysis on that particular part that I won't share due to time constraints, but it's more to reinforce the point of how we are deploying and providing feedback to students. So hopefully that was of interest, and maybe some of the pink collaborate points were relevant to you. We've got some more information that this QR code or this URL takes you to, so please follow up. So if I could summarize, I've been talking about providing automated feedback on impasse-driven self-study, so students getting stuck and getting some help. It's a lot of it's based on evaluating student answers to tasks, but as you saw, also looking at method as well, and hopefully more of that in the near future. And we've developed this platform called Lambda Feedback, which I conceive of as the plumbing, to allow teachers to deliver feedback to students, allow students to access their tasks. But it's built with a microservice architecture so that the feedback itself is external and there's a very low barrier to entry to anybody developing a feedback algorithm in any language, on any infrastructure, and deploying that on the system that we've built, Lambda Feedback, but also on other systems that exist. And we're collaborating on standardizing that API so that anyone who's making one of these algorithms can get as broad a reach as possible. Because I think as a sector, we need many such algorithms. And so we need routes to use, as it were. And so to illustrate some of this, I've shown two case studies. One is on comparing two algebraic expressions for equivalency or equality, and trying to qualitatively understand the difference to the extent that we can give good feedback. And then on the written proofs, that's more LLM driven. So in future, as I mentioned, we want to develop this standardized interface so that all of these microservices can be called very easily. That's basically to facilitate innovation. And we will always be developing new algorithms and evaluating how they perform. I didn't do any detail on the chatbots, but that is something we're working on as well. And then, of course, concluding the presentation where I started, which is that this is about feedback to students. Ultimately, we want to know what impact is this having on their experience and their learning, and that is much more early stage, that kind of research. So thank you very much for having us and the opportunity to share with you. I look forward to questions.
Okay, thanks very much. We could show our appreciation with a round of applause there, please. And I'll open up the Q&A, see what we've got. So we've got one question so far. If other people want to put some more questions in, that'd be great. So to what extent do you intend students to use these tools? It's quite a long question, this or a number of multi-part questions. So this is from Tom. To what extent do you intend students to use these tools? Could some of the automated feedback include a recommendation to talk to a human for support? Interesting idea. Otherwise, we could end up in a situation where students are even less inclined to ask questions in tutorials, seminars, etc., when they are stuck. So a couple of questions there. Do you want to?
Yeah, thanks, Tom. So there'll be a range of intents depending on the teacher, but the general idea behind this is to conceive of feedback on different levels, like following Hattie's feedback model. So task level, process level, and self-reflection. And this is task level feedback, which we often find students, if they get it by the time they come to a tutorial, it could be too late, or they've forgotten what they were doing, or this kind of thing. So it's that low level feedback. I think it's also frustrating as a teacher when you spend a long time and then realize they had a sign error and think, couldn't that have been done for them? So we're looking at automating that low level, task level, automatable part. And because the contact time between the staff and the students is usually one of the bottlenecks, the idea is to enhance that contact time by getting to deeper questions. So I found out I was wrong and I fixed something. I found out I was wrong and I fixed something. And then eventually I got to the point where I thought, I don't even understand what's happening. And at that point, that's a good time for a human level conversation. So the idea bears your question in mind and is well intended to enhance the value of contact time. But I do recognize the risk that you articulated there, of potentially having negative side effects. And that's why I kind of ended with the question of what impact is this really having on the students? And so I see a lot of positive impact. We get a lot of positive feedback, but I think we could and should be more rigorous than that. And then in that sense, the answer is, I don't know at the moment. And that's something we need to look out for. And if anybody wants to help look into that, then that would be good.
Okay, very good. So Tom said thanks. Basically, that makes sense. Thank you. So, I also see that Tim's got a hand up. I was wondering if you could put the question in the Q&A for us, because I've got another question here, which is actually in the chat. So I'll ask that first to give Tim a chance to put something in the Q&A. So can lecturers in institutions sign up for the platform and use it in their teaching? Will I be able to use the platform from Canada?
Yes. So the short answer is yes. We're kind of, when things are going wrong when you're building it, you don't necessarily want to share it with anyone else. But we've kind of been through that phase, and we're quite keen now for other people to use it. So the answer is yes. And if you follow up with me, then we can discuss. But we have got other people in other institutions using it. We've done a demo in a school and some universities. It's very early days for those external users, and I welcome more people who are interested in that.
Because I was wondering how people would get involved in this. I mean, they just write to you.
Yeah, at the moment I lead the project, and you can write to me, and that's the best way to do it.
Right. So there's nowhere online where we can go and just play around for a little bit.
Yeah, we don't. All of the algorithms are open source in our GitHub repository, so you can, for example, clone them and run them and see all the test cases and try your own. So if you're interested in the algorithm side, you can just do that. In terms of the platform, you can log in to the platform. You can go to lambdafeedback.com and log in, but you won't see any modules there. You'd have to be added as a user. So then if you contact me, then we can add you as a user, and then you'd be able to use it. It would be nice if we had a public web page where you could just try it out, and that's just kind of on the long to-do list. And as that doesn't affect our current users, it's just not what we've prioritized. But I'll take that away as feedback that we should make one of those.
Yeah, because that's what I was thinking. I mean, your answer of saying, oh, you can go to GitHub and clone it, and I think that immediately is a big barrier for a lot of people. Whereas if they could see it in action to begin with, that'd be good.
That's a good point. Thanks, Kevin.
Right, I think we maybe got one more chance for one more question from Tim. He's put it into the Q&A. So Tim says, as a software developer, I like your answer. We're not quite sure what that's referring to, but it says, as a Stack fan, I don't understand why you would start writing a new algebraic equivalence evaluator from scratch rather than just plugging in the Stack API or numbers. Yeah, I was wondering that as well. You seem to be there's a lot of people have put a lot of thought into that part of the analyzing what's gone wrong, or whether it actually is the uh, same expression, shall we say?
Yeah, thanks. This is a good question. So where this comes from is we were using Mobius, so we were programming in Maple, which wasn't something that we used except because it's what's in Mobius. We didn't have access to Stack because we didn't know how to kind of run it ourselves, and we didn't have Moodle in our institution. So I've never actually been able to use Stack. Otherwise, we would have used it. I've been in touch with George Kinnear, who's helped me kind of understand what it does and showed me the source code and where these kind of lines are that do the comparisons. But I don't fully feel able to try that out, and I would like to know more. So that's kind of a lack of understanding on my part that I'd like to resolve. But what we felt was that Stack uses Maxima and Mobius uses Maple, and it goes on like this. So we wanted to decouple that and say it shouldn't. If you want to solve a computing problem, you should do it in a way that you see fit, depending on the problem and the tools that you prefer to use, and that should be decoupled from the platform. So what we'd like to do is take the work that's been done in Stack and make it available in this kind of way so that we can benefit from it. So it's a kind of an architectural pitch that gets at the fact that platforms and languages are usually coupled, and we wanted to decouple that. So it's kind of an answer and kind of an apology, I think.
Right. Okay. So, I think it's a good point to stop there. Tim has clarified that first sentence about as a software developer, I like your architecture. So it looks like that was an autocorrect,
Yeah.
which is quite fitting for the question he was asking, really, about
Yes. Yeah.
you type things in. So yes. Okay. So can we just everyone once again round of applause. There's the React button to use that. And can I thank all our speakers today for this very interesting set of talks. And I think that's it for the Talmo today.